All right, today we're pulling back the curtain on one of the most invisible yet most powerful parts of architecture, acoustic design. And we're not just going to talk about it. No, we are going to design and build a virtual auditorium right here, from the ground up, using the real rules and numbers that architects work with every day. So grab your virtual hard hats, because construction starts right now.
So, have you ever really thought about that? Why a concert hall can feel like you're literally wrapped in this beautiful, warm sound, but a gym is just a chaotic, roaring mess of echoes? Well, the secret, it's not luck. It's all about physics, meticulously engineered. And today, we're going to be the engineers. So here's our game plan for this explainer. First, we'll dive into the architect's acoustic rulebook. Then we'll get our hands dirty designing by the numbers. After that, we'll pick the right materials to really sculpt the sound. And finally, the big moment, the final sound check, to see if we nailed it.
All right, first things first, the rulebook. Look, before we can even think about building, we have to learn to speak the language of acoustics. These are the absolute fundamentals, the physics that control how sound behaves in any space.
Okay, the single most important concept, and I mean, if you remember one thing, this is it, is reverberation time, or TR for short. Just think about it like this. You clap your hands in a huge empty church. That sound just hangs in the air for a few seconds before it fades away, right? Well, that little bit of time, that is the reverberation time. It's literally the acoustic signature of a room.
But here's where it gets really interesting. There's no such thing as one perfect reverberation time. It completely depends on what the room is for. You know, in a lecture hall, you want a short TR. That way, every single word is crisp and easy to understand. But for a big symphony orchestra, you want a much longer TR, so all that beautiful music can swell and blend together. Now, to control that sound, architects have two main tools in their toolbox. First, you've got sound absorption. This is all about what's happening inside the room. Think soft materials, things that soak up echoes. Then you have sound insulation. That's the barrier to the outside world, using thick, dense materials to stop noise from getting in or out. So one sculpts the sound inside, and the other one protects the space from the outside. Okay, enough theory. It is time to build. We are now officially designing a 2,200-seat multi-purpose auditorium, and we're going to do it using the actual formulas that architects and acousticians use every day. So, how do we start? Well, there's a process. We'll kick things off by setting the floor area, which lets us calculate the total room volume. That's a super critical number for acoustics. From there, we'll figure out the actual dimensions. And then we set our big goal, the target reverberation time. That's our bullseye.
Let's start plugging in some numbers. We're starting with 2,200 seats. Now, a good rule of thumb for architects is to budget about 6.5 square feet per person. That gives us a total floor area of 14,300 square feet. But for music, sound needs air. It needs space to develop. So we multiply that by a standard volume per seat factor, and we get a massive 484,000 cubic feet of room volume to play with. That is a huge space.
So what does 484,000 cubic feet actually look like? Well, in our case, it's a room that's 120 feet long, 96 feet wide, and 42 feet high. And hey, these ratios aren't just pulled out of a hat. They're specifically chosen to avoid something called standing waves, which are basically these really annoying acoustic dead spots or hot spots where certain sounds get trapped and just buzz. So there we have it. The shell of our virtual building is complete. Okay, time to define that acoustic bullseye I mentioned. Since this is a multi-purpose hall, for talks, for concerts, we need a good balance. We are officially aiming for a reverberation time of 1.5 seconds. Every single decision we make from here on out, every material we pick, is all about hitting that one specific number. So we've basically built a giant concrete box, and right now it's just a massive echo chamber. To make it sound truly beautiful, we need to pick the right stuff to put on the inside. This is the fun part. This is where we stop being builders and start being sound sculptors. Okay, so we run the numbers on our bare bones shell, just concrete and gypsum board, and Houston, we have a problem. The calculated reverberation time is 1.92 seconds. That's almost half a second too long. The room is way too live, way too echoey. We've got to tame this beast.
So how do we do that? Well, we use a whole palette of different materials, and each one has something called a sound absorption coefficient. It's really just a simple score from 0 to 1. Think of it this way. Something hard, like painted brick, has a score close to 0. It absorbs almost nothing. But then you have materials like heavy carpet or special acoustic panels. They're like sound sponges, just soaking up all that extra acoustic energy.
And you wouldn't believe the power of picking the right material. I mean, it is staggering, especially when we talk about insulation. Take a standard brick wall. It might block, say, 37 decibels of sound. But if you add a proper insulation system inside that exact same wall, the rating can jump all the way to 58 decibels. That is a night and day difference. It's the difference between hearing traffic and total silence.
And you know what? It's not always about using some fancy, expensive material. Even really simple choices can have a huge impact. Just look at this. Using 2 layers of standard gypsum board instead of 1, that can boost a wall's sound blocking performance by 8 decibels. It just goes to show you every single surface and how you build it matters.
Okay, let's recap. We know the problem. Our room is way too echoey. We know the solution. We need to add materials that absorb sound. So now it's time to put it all together. We're going to strategically place our sound-absorbing surfaces and run that final calculation. The big question is, did we nail it?
Well, the math tells us exactly what we need to do. To get our reverberation time down from that echoey 1.92 seconds to our target of 1.5, we need to add 3,550 units of sound absorption. And that unit, by the way, has a name. It's called a Sabin, named after Wallace Clemens Sabine, who was basically the father of architectural acoustics.
So, what in the world does adding 3,550 Sabins actually mean in the real world? Well, it's pretty simple math. Let's say we pick an acoustic tile that has an absorption coefficient of 0.67, so it's a pretty good sound sponge. To figure out how much we need, we just divide the Sabins we're short by that coefficient, and boom, the math tells us we need to cover about 5,300 square feet of our room's surfaces with this stuff. Think the back walls, parts of the ceiling, that's where it'll go.
All right, so we've done it. We've defined the shape of the room. We've calculated exactly how much absorption we were missing. We've chosen our materials, and we've figured out precisely how much of them to use. We have followed the rule book to the letter. So the only question left is, after all of that, did we actually hit our target?
Yes, we absolutely did. The final calculation, with all of our new acoustic treatment plugged in, shows that the new reverberation time for our 2,200-seat auditorium is exactly 1.5 seconds. Perfect. We've just designed a beautifully tuned, multi-purpose performance space, and we did it with nothing more than a set of rules and a calculator. How cool is that?
So, the next time you walk into any room, a concert hall, a classroom, maybe even just your office, do me a favor. Just stop for a second and listen. Because you're not just hearing sound bounce around. You're hearing hundreds of invisible design decisions. You're hearing the choices that an architect made to shape your experience. You're literally hearing the architecture.